Right now, out in the elements, a frosted brass safety valve is violently venting highly compressed gas directly into the open atmosphere. The multi-trillion-dollar artificial intelligence boom relies on a physical process it cannot code around: extreme heat transfer. Out in the open ocean, massive commercial shipping tankers are idling, trapped by global shipping blockades. With every day they sit motionless, the cargo inside their hulls slowly warms and boils, forcing pressure valves to release it. An irreplaceable asset is actively destroying itself miles from shore, triggering a severe supply shock on the other side of the planet. The global tech economy is currently bound by the unyielding physical leak rate of a non-renewable geological asset. To understand why this is happening, we have to look inside a modern semiconductor fabrication plant. These immense lithography machines dwarf the engineers operating them, and they require highly controlled environments to function. The process inside, known as extreme ultraviolet lithography, uses high-energy plasma to carve microscopic patterns into silicon. That reaction generates massive amounts of heat, which must be instantly removed to keep the system stable. Engineers manage this thermal load using an electrostatic chuck. A liquid coolant is injected directly beneath the delicate silicon wafer to draw the heat away. That coolant is liquid helium, specifically grade 6 purity liquid helium. It is the only substance on Earth capable of surviving at -269 degrees Celsius without freezing solid and destroying the internal machinery. If lower-grade coolants are used, trace impurities enter the system. Even a few parts per billion will trigger localized thermal hotspots, causing the silicon wafer to warp at the nanometer level and misaligning the intricate transistor patterns. Without a continuous stream of pure liquid helium, the thermal load inside these machines rapidly exceeds safe operating limits, causing high-precision components to lose their alignment and bringing the production of sub-nanometer transistors to a total halt. Supplying that flawless stream requires extracting the gas from deep underground deposits, heavily concentrated at massive industrial processing ports in the Middle East. Once liquefied, the helium is loaded into specialized cryogenic containers. They use vacuum insulation and liquid nitrogen shields to keep the cargo frozen. But these containers operate on a strict ticking clock. They can only maintain those deep cryogenic temperatures for about 35 to 45 days. This chart maps the internal state of a standard ISO container. As ambient heat slowly penetrates the shielding, the internal temperature curve inevitably rises. Pressure builds until the safety valves trigger, actively venting the boiling helium into the sky to prevent a catastrophic rupture. During the early 2026 shipping blockades near the Strait of Hormuz, these vessels were forced into a massive detour. Rerouting around the Cape of Good Hope adds roughly 20 days of continuous travel time. That delay stretches the total transit timeline well past the 35-day thermal limit. The extended journey completely exhausts the pressure limits, forcing the remaining liquid helium volume to drop to zero. This is a logistical crisis that cannot be solved with money. The time delay literally forces the vital commodity to evaporate into thin air. This fragile logistical network stands in sharp contrast to the foresight of the early space race, when the American government recognized the absolute necessity of a domestic safety buffer. They built the National Helium Reserve in Amarillo, Texas. It was an impregnable geological vault designed to hold billions of cubic feet of gas and protect national security from global supply shocks. Decades later, the Helium Privatization Act of 1996 shifted that mandate. The legislation required the sell-off of the stockpile to pay down the immense bureaucratic debt the facility had accumulated. By 2024, the final assets were quietly liquidated. The domestic buffer was completely dissolved, transferring the entire risk burden to the volatile private market. By liquidating a Cold War-era strategic stockpile to erase paper debt, policymakers systematically dismantled the primary buffer meant to stabilize the U.S. semiconductor supply chain during a global crisis. The fallout hit the supply chain in mid-2026. Without incoming shipments, South Korean and American semiconductor fabs burned through their tiny 30-day safety inventories in a matter of weeks. Operational paralysis set in. As fabs attempted to stretch their remaining coolant, thermal hotspots went unmitigated, causing wafer defect rates to skyrocket on the assembly lines. The damage cascaded outward. Hard drive manufacturers, who rely on the gas to seal high-capacity platters, were forced to institute immediate, massive price hikes just to survive the shortage. Unlike software code or silicon architecture, liquid helium cannot be synthesized in a lab. It is a finite product of deep geological radioactive decay, extracted slowly from beneath the Earth's crust. And because it is the second lightest element in the universe, once it escapes a venting pressure valve, it drifts upward, past the atmosphere, and permanently fades into the pitch-black void of space. The current era of high-end computing exists within a thermodynamic boundary, dependent on a singular geological resource that, once released, escapes Earth's gravity forever.